So I'll basically give you an overview of this project that we're talking about today, which is Phoenix Apartments. So just to give a bit of a background, as Andrew mentioned, I'm from TTW, so we're one of the largest independently owned structural and civil and traffic firms within Australia. We have 230 staff, and we have offices here in Melbourne, where I'm based, Canberra, Sydney, and Jakarta. So just to give you a bit of ideas, we've actually got quite a few timber projects that we've done. So one of the ones that we do at the moment is here in Melbourne. We've got La Trobe University student accommodation, which we did with JCB Architects and Multiplex. So this one's pretty close to being completed. This is a CLT floor and wall building. Then over in Sydney, we've got the Bond Norwest, which is I think it's a 7-story office building, and consists primarily of glulam frames and CLT flooring. Then you've got St. Kevin's Resource Centre, which is another one here in Melbourne, which is a CLT slab with a big steel transfer structure over an existing pool building. And then over in Canberra, we've got ANU, which is a glulam beam and column with a CLT slab and then a PT transfer system. Some other ones here in Melbourne is Brandon Park Primary School. So we've got quite a few schools that we're doing here as part of the VSBA projects. And then over in Sydney, there's Ganyama Park Aquatic and Recreational Centre, which is known to have 50-metre long steel trusses that support these 36-metre long glulam mass timber beams. This project, I think, is actually almost near completion. So hopefully you guys will get to go out and see that soon. Some of the ones that we've done ourselves include Bunjil Place here in Melbourne, which I think is one of our probably more well-known ones, which has this beautiful timber grid job. The Macquarie University Incubator, which is obviously over in Macquarie Uni. So this was designed as a temporary, as a quick build. It was, I think, put together in a bit over 30 days. And then you've got Melton Library here in Melbourne as well, and then Our Lady of Assumption Catholic School in Sydney. AVO Norwest, which is probably our first major CLT project that we did with Strongbuild. It was a 9-story building using mostly CLT construction. We've got Phoenix Gallery, which is a very fancy lobed system using CLT, and then there's Taronga Wildlife Zoo Retreat, which is basically a new accommodation precinct with 62 guest rooms spread throughout 5 accommodation blocks. So just today, I want to give you a little bit of an overview on the building, and it's like Andrew said, just give you a bit of an introduction to the project itself. So the people who worked on this building were myself, who did a lot of the day-to-day design. It was Raj, who was one of our senior engineers, who also worked on it, and our director, Kevin, who basically oversaw the building. So this is what it looks like now. This was actually completed in 2019, so basically last year. It's a second phase of a new development over in Rouse Hill, which called Parkland Estate. And the first stage was a townhouse development, and then the final stage includes a new building called Lotus. So we were engaged by Strongbuild as a D&C structural engineer for the project, originally brought on in 2015. So the project is, as I mentioned, located in Rouse Hill. So if you, for those of you who don't know Sydney, it's located north to the northwest of the CBD in what is a fairly rapidly developing area. The location of the project is actually at the end of the new metro line, so near Tallawong Station, for those of you who are aware. So that's basically why it was constructed around there to align with the new metro. So it's basically split into 2 stories, 2 buildings. One of them, the western one, building A, is 5 stories, and then you have building B, which is a 6-story building. The timber was erected by Strongbuild. The CLT is sourced from Binderholz in Germany, and then the LVL is sourced from Westbeam and Dindus. And as mentioned, it was completed last year by Westbourne, who took over after from Strongbuild. So this is the basic structure here. So you've got a concrete podium PT slab. Underneath that, you've got concrete basement with a slab on ground basement car park. There's LVL stud wall that forms part of the lateral system as well as the vertical load carrying capacity. And then you've got CLT floor panels, and there's CLT lift and stair cores as well. So a lot of these stair cores were actually exposed on the inside. That's why they wanted to build them out of CLT, so they basically became a bit of a feature for the building. So the floors were constructed of cross-laminated timber. The reason for this was one, it was just nice and simple to construct. The walls also act as a diaphragm between lateral load resisting elements, i.e. the stud wall. So in this building, the stud walls actually resist all of the lateral loading. The cores don't actually do very much in this building at all, interesting enough, which I suppose is different to a lot of other buildings that you might think of. We had to check for vibration, which we did against the criteria in EC5 or Eurocode, and also performed some FEM footfall analysis as well. So for areas within the walls where we had large openings, say for a big door or window, we use a steel beam to basically carry through over the large openings. So these are the prefabricated timber walls. So originally the building was supposed to have CLT, or was designed with CLT walls, but this was then they were then replaced with prefab stud wall made out of high strength LVL. And the intention for that was to try and save volume and achieve a cheaper cost, especially since the walls were covered up and not exposed. So they consist of LVL stud, and the reason this is to allow it to achieve a greater height than what you could construct out of MGP10, and it also allowed us to basically pre-make all of the walls within the factory, and they would put a lot of the services in there. They then cover it with OSB or plywood, and then they plasterboard line the whole thing to try and fire protect it. So once they brought it over to site, they could just basically sit it into place and move on to the next section. So making it nice and quick and easy. We use clusters of studs at the ends of the walls, so to carry concentrated loads, say over where there were lintels or steel beams for openings. And the reason for this was just to try and make it as simple as possible, really, and to integrate that within the wall structure. So as I mentioned, the walls were actually the main load resisting, the lateral load resisting element within this building. So obviously when you have a lateral force, you generate tension and compression loads within the ends of the building, the ends of the wall. So we had grouped studs at each end to basically take out the compression force, and then the tension reaction was resolved using this proprietary tie-down rod system developed by Simpson Strong Type. I think it's a strong rod system. As you can see, this is the little diagram on the right of how it works. Basically, it's anchored down into the PT podium slab, and then it allows it to basically hold down the wall and prevent it from going into uplift. Obviously, because the walls go, well, lateral load can go either way, you have to have one at either end of the wall. There was obviously a lot of connections within this building to try and tie everything together. The connections consisted mostly of proprietary bracketry supplied by Rotherblast, as well as a great deal of screws, which basically held everything all together. We were using that to tie floors into walls and walls into other walls and so on. And then we had these shear brackets at the bottom of the walls to try and take out the shear load from lateral forces. So when we designed the walls, obviously you have wind loading. So we had to check these stud walls for lateral deflection under service wind cases. And then under seismic, we had to ensure that there was enough ductility within the system to allow for our overstrength mechanism to basically our load hierarchy was actually properly fulfilled. So what we actually did for this one is Strongbuild wanted to use a series of staples to build their walls. So we actually had some tests done by NSW to verify the capacity of the walls as well as the ductility performance, which I'll touch on a little bit later. The things that we need to consider, obviously it being a timber building, were durability. So for that, one of the major things is termite damage. So a lot of the stud walls were actually treated internally to protect from that. They also, obviously covering it in plasterboard lining also ensured that it would work protected under a fire scenario as well. The materials, as we said, the CLT was provided by Binderholz and it came from Europe. Obviously, what this meant was we needed to lock down the CLT design a lot earlier so that they could get it shop drawn and shipped out from Europe in time. The LVL was locally available, which meant that we could take a little bit more time to refine the wall design and make sure it was as optimal as possible. There are obviously buildability concerns. What we had done was we tried to minimize the change in floor thicknesses, because then this would simplify the detailing and the junctions between floor panels. So we basically stuck to 3 sizes. We had 100, 160, and 180 thick floors. So 100 was generally used within the corridors. 160 was used for the most of the floors, and where we had certain areas where we had higher loading or we had excessive spans, and we had a thicker panel used instead. There was a lot of standard connections and lots of screws and bracketry, which was just there to simplify a lot of the on-site connections and just make it as easy as possible to put together. Some of the areas where we had clusters of studs, there was concern, because this is a platform construction, as you see, and the floor goes through the walls, there's issues where when you have a huge amount of studs carrying, say, a steel beam at the end of a wall, at the end of a large opening, and we had a cluster of studs that are maybe 3 or 4 studs sitting next to each other. There's a very large crushing force on the floor through there. So there were some sections of the CLT floor where we reinforced it by basically cutting a little block out of the CLT floor and sticking an LVL piece in there, which I think Andrew will mention a bit later, that had an influence on the axial movement. So as it was a panelized wall system, we had to make sure that we allowed for the manufacturing process. So things like ensuring there's enough tolerance so that when they're building these things in the factory, that they can match within what the machines are capable of doing in terms of the tolerance of where they place staples and how thick things need to be and so on. Because it was prefabricated, the other advantage of that meant that they could be pre-finished in the factory, and again, meant minimal sort of on-site work. You don't have to have someone walking around on site erecting plasterboard or stapling plasterboard onto it. The other advantage was that they didn't need to have a lot of the noggings in the wall, because it meant that the sheathing was already straight onto the wall at the time, and it provided stability to the wall for the transportation and erection purposes. We needed to inspect a lot of these walls, obviously, so we did a lot of visits to the factory to try and make sure that they were being manufactured properly. So i.e., the staple spacing correct, is we're not making sure that staples are not overdriven within the OSB itself, and just making sure that everything's basically come together as it is and there's no strange surprises. From a fire point of view, we had consideration for 1720 Part 4, which talks about charring on cross sections. Generally speaking, though, we used plasterboard to protect the timber stud walls under a fire scenario. So there was actually 2 layers of plasterboard on each side of every stud wall to protect it for the full 90-minute duration. Then for the CLT, we also used plasterboard, and that was a tested system done by CSIRO, which was basically a combination of plasterboard lining and then charring to achieve the full 90-minute duration. So for axial shortening, which is kind of what I think what Andrew mostly will be talking about, we had to determine that. So things like the facade gaps and things like, when they installed services, that there wasn't too much differential movement between everything, and making sure that we weren't going to cause issues with the facade because the building has started to move and the gaps in the facade are not capable of tolerating that kind of movement. We generally left a bit of space at the top and the bottom of the walls to prevent OSB from being from shortening and being loaded up directly when you stick the CLT on top. And that's because when you've got when we place the OSB and the plywood onto the wall in the factory, there's no load onto the wall. And so when we then load up the wall on site, we don't want to have a situation where the plywood is potentially taking some of that vertical load. To avoid differential shortening between vertical elements, we also tried to avoid placing vertical steel elements and then vertical timber elements right next to each other. So as you can see here, as I mentioned, we had group studs. So this is an example on the right here, where we basically increase the number of group studs under the steel beams to carry the load. And this way, we allow for compatible axial stiffness between different elements. So as I mentioned, the stud walls we actually designed to 1720 Part 1. The crushing of the LVL bottom plates actually governed the design in this case. It wasn't actually the buckling of the studs. We used staple connections because it was chosen from a manufacturing perspective, because it was a lot faster for a machine to go around and shoot a bunch of staples into the sheathing as opposed to having a nail gun do it. So that was what caused the need to start testing some of these walls, because staples were not as, I guess, well understood as nailing. So we did some of the prelim checks on the staples against Eurocode 5, and then the capacity of the staples was then confirmed by full-scale wall testing that was done by the University of New South Wales, and that was just to verify the strength and ductility assumptions that we had made, to ensure that we actually, like when we were allowing our seismic loads to be reduced, assuming ductility, we needed to obviously fix the loop and make sure that the system actually had the ductility that we were assuming, and we weren't potentially under-designing things. So from the site phase, things were sort of straightforward. A lot of the things the floors and walls came to site, all pretty much all pre-done, prefabbed. They had temporary pops to support the walls until they got the next floor on, and then just down, and then obviously they take those props, put them onto the next floor, and just cycle them through each floor. So this was what the building kind of looked like midway through construction. It was actually, this area looks quite different now. Actually, there's a lot more buildings around it, but yeah, it was quite interesting. At the time, it was really in the middle of nowhere, but now it's quite a bit different. So one of the main things, I guess, that we learnt throughout this process was just making sure that we allow for manufacturing needs early in the design approach. So this was things like standardizing the stud wall sizing, so that when they're trying to build a wall, they're not having to pick, lots of different studs out of a lineup. So trying to simplify everything and make it as uniform as possible. And obviously also allowing for consideration of manufacturing tolerances, so that if there are issues with installing studs and so on, that we don't have problems there. The edge distance requirements for the sheathing, so the OSB and the plywood, was critical. So we had to make sure that the plates were thick enough, and that when they installed the staples, there was enough edge distance for that to still work. What we found generally was that it was more practical to utilize more material to get better, more practical details, and this actually led to a better design approach. So the design philosophy for dealing with the lateral loading needs to be consistent across all elements. And obviously we need to check the crushing of the floor panels, as this is often what's actually critical. Sorry, one second. And then obviously the effects of differential axial shortening should be minimized by not having different elements placed next to each other. So that's pretty much everything from my end. So Andrew, if you want to take back over and start your bit.
So firstly, I'd like to just acknowledge the people that were involved. We had Strong Build, obviously, who allowed the technology to be installed in this building in the first place, and the company which the technology came from, Structural Monitoring Technology from Canada, TTW, and Wesbourne Construction. So why did we monitor a building? There's a number of reasons, and the main one is what Simi's already alluded to, is that the axial shortening differential movement was a key consideration, and as you saw, it was to govern the sizing of elements in the building. So what causes movement within buildings? There's elastic compression, creep compression, deflection of horizontal members, both the timber and support structure, and creep deflection of those horizontal members, again timber and support structure, and shrinkage and expansion. So as engineers, we need to get an understanding of how much that occurs. And just a reminder, this is just a common thing for all building materials. So most of those actions, other than probably shrinkage, is common to all building materials. So for timber systems used in mid-rise buildings, this is a relatively new concept in Australia. And traditionally, timber design for houses, which is governed by the Australian Standards AS 1684, most of those things are accounted for within the code. So, but mid-rise timber buildings, particularly timber frame, is nothing new. It's been used in North America and Europe for a long period of time, and they've generally got around these issues. But for Australia, our climatic conditions and timber species are different, and it was a bit of a consideration, are we going to get the same type of results? So what we're trying to do is probably validate some of the assumptions that the Northern Hemisphere would use and is applicable here. And to also input in a wood solutions guide number 50, which is a mid-rise timber building structural engineers guide. And in that guide, there was a need to make some assumptions. And so we have a calculation methods, which I'll talk about very shortly, and there's obviously assumption goes with it. These calculations rely on assumptions that were relatively untested in the Australian context, and that was the reason why we needed to get some real data against this. So settlement building components, there's quite common things such as closure of joints, and there's a picture of an overseas building here, and you can see there's quite loose gaps between the elements, and when you just imagine you put more load in the building, they'll close up. Also the deflection of the support structure. In this case, is the actual project at Rouse Hill, and you can just imagine there's a fair bit of gaps because of the deflection in the concrete slab. So in the wood solution guides, we assume for prefabricated elements 0.2 millimeters, and for site built elements 0.5. And you can see on the picture on your right, there's a number of opportunities for gaps to occur in timber frame buildings, and imagine this over 6 stories. So you add those up. So there's an equation there in the guide, and I won't go into detail what that is. But just to remind you that the substructure, you calculate it for its normal calculation means, but remember they generally have greater spans and therefore more deflection, and there's also creep. So you can account for some of that deflection by packing the underside of grout between the wall and the slab, but you'll get creep occurring as well. So calculation of timber deflection in horizontal elements, pretty much normal manner here, just using the appropriate load case. So they can be reduced by aligning studs in the wall frame, so they transfer through, so there isn't any parts to deflect, or use whole type of framing techniques called balloon framing. The one which, as Samid said, was the criteria was the bearing of horizontal elements and wall place and joists and things like that. In this case, CLT floor. That is something which is where you get occurs, and obviously occurs all horizontal members. Another presentation we'll talk about perpendicular grain type issues. And here's what could happen, and this is a loaded test which was used to investigate bearing type of issues with timber frame, and this is pretty much like what was done in the building, a plate with LVL studs. So perpendicular grain deformation, there's an equation in the guide, but the compression loads are cumulative, so it needs to be calculated per floor using your small loads. But the MOE perpendicular grain is an estimate, and it's based on stress grade parallel to grain, and it's been found in recent research is not quite correct. There is a method which is contained in a report that TDA did, which is available from Wood Solution, available from Forest and Wood Products Australia's website, and it talks about the bearing capacity of common Australian imported timber species, and it does give a better way of estimating the perpendicular to grain MOE. Just to remind you that the bearing check that you have in 1720 Part 1 is a pass-fail criteria, and it's not, well, this issue is more of a serviceability issue. So you'll probably find that be wary that 1720 is used is not going to give you the idea of how much movement's occurring in the building. Compression of vertical elements, obviously studs, there's obviously a bit there, but you can just imagine there's not going to be that much for it. But the other area where it's going to be mainly seen is in the shrinkage of the vertical elements. again, it's fully along the grain. It's 1/40th of the tangential movement for the species, and it changes for in-service moisture content, which we'll talk about more later. And you can see it's a very small number when it comes to timber along the grain. Not so with shrinkage horizontal to the grain. We have again the same type of things. It was the moisture content, but you can see here that the number is quite large, and when you add up all of the millimetres which are in the horizontal plane. So that's why you might hear us from time to time as I shake out the horizontal elements out of your building or your load path, and have them bearing vertical on top of each other is a better solution for these sort of buildings. It reduces the amount of movement going to occur. So which solution guide has a number of suggestions. So it has suggests that during a rain is during construction, which it always does, then the MC of your timber may change from the target EMC, and I'll talk about what that is later, to about 16%. But note that's for sawn timber size elements, but not so for mass timber. There will be a moisture gradient through the mass timber from the surface of the outside of lamination to the centre. So just think about this. This is from Swedish wood. Nice illustrations. Your surface moisture content might be 7%, but the centre may be 21%, and we really talk about it an average. So just be wary that there is a change, and we'll talk a little bit more about where we measured in this building. So equilibrium moisture content, and just a reminder and a heads up, it's a CPD question. So equilibrium EMC, we'll call it, is the moisture content at which the timber neither loses nor gains moisture from the surrounding atmosphere, the Goldilocks condition. And generally for major Australian cities, we assume an EMC of about 12%. But this EMC may be lower if we use AC or heating for extended periods of time, or the building is located in a drier region of Australia. Therefore, we're assuming that the 4% moisture content change, is this correct? And remember, we have other issues such as creep, so we use a J2 factor of 2, so creep doubles reflection and compression estimates. So we kind of like tick through the major ones that cause movement within timber buildings, and we're just seeing, we have assumptions in the Wood Solution Guide 50, do they actually bear out? But also a reminder they have other reasons that cause actual shortening of movement. Is, for example, of using acoustic strips, such as this image here of a CLT building. They will compress, and those dimensions should also be included. So, why in summary? Mid-rise timber buildings are relatively new. Climate and timber species are different to international experience. Assumptions used within Wood Solution Guides are based on best practice international experience. And just to remind you again, is moisture content change from 16 to 12%. And design assumption that each story will move around about 6 millimetres, 1/4 of an inch. That's showing where it's come from. So it's a US practice, and it's something for the engineers out there. When you do some calculation in this area, it's not a bad thing to include these assumptions on your design drawings. So if you assume allow 6 millimetres to occur per story, then it'd be good to inform it on the structural drawings, so your follow-on trades know that they should allow that type of movement within plumbing and other bits and pieces that may suffer from some form of movement. So what we're doing is validating key assumptions used within this Wood Solutions Guide. So how much movement really occurred? It's just a little bit of reminder about the project. So I just clicked through this because we saw the same photographs from SANID, and remind it there's prefabricated panels and the finished building. And another CPD question: the building uses a CLT floor. So what and how is the building being measured? So we're measuring it vertical displacement, temperature, relative humidity, and moisture content. And whereabouts, this is a floor plan of the building in the corner of it, and we're measuring it on the east side external wall, near the corridor, the inside of the apartment, and on the south side of the external wall. And we look at the building itself. That's the east side, the corridor wall, inside the apartment, and the southern side wall. So we measured that as a slice through the building. So each one of those points, we measured that 6-story and 6 stories. And this point of the building, this is where the building was 6 stories high. So sensor and data logger are used. We we purchased this online from Structural Monitoring Technology from Vancouver, Canada. So why do we purchase this type of stuff from overseas? That's why, because they have off-the-shelf systems, and they can help monitoring the and they've actually had a number of buildings using their technology. So we're actually just borrow from their experience and they'll apply to Australia. It was just really easy because they've done all the hard work, and we just purchase the equipment and just install it. They had a software which was cloud-based that just allowed us to analytically sort it out via the internet, which made it really easy. So they have done a number of buildings. If you go to their website, and you'll see some reports on some of the buildings that have been measured in Canada. So it's a good experience to compare how our results have gone and compare to theirs. So vertical displacement, we use a thing called string pots. The string pots are nothing more than a wire which connects from each floor above to the floor below, and they've leapfrogged up the building, and so you get so 6 stories with 6 of these string pots, and the spectrometer, which measures the resistance. So as the building moves, a circular dial moves, and that is calibrated back to movement. We use a high technology here, so we use a tracer line for fishing hook, which was used to connect it because it did not elongate compared to using a weaker wire. So these were installed into a tube or a conduit, and the conduit was designed so it allowed to move. So it was an oversized conduit on top of the central main conduit. And the reason being of that, you see here with the picture, is that there's obviously insulation and things that are going to go in the wall, and so we didn't want to interfere, or the wire to be interfered with by other things that may appear in the wall. Also, we were penetrating the floor, and we needed to have a penetration seal there as well. So moisture content and temperature, they were just measured by the usual pin sensor, so point moisture measurements. It's nothing more than gauging electrical resistance or temperature between screws, and the temperature was also measured as a means to correct for species moisture content, automatically done by the system software. We use a shielded screw exposed points, which was 17 millimeters deep, and this was a midpoint into a dummy stud. We use a dummy stud because the structural timber framing couldn't be measured because it was prefabricated and enclosed when it was delivered to site, and the rest of the partition walls and external walls was steel framing. So we placed into the steel framing elements the dummy stud and measured that, and it's nothing more than a piece of radiata, 70 by 35, and we also occasionally use spruce to see if there's a difference between the two species. We're talking about later. We seal the ends of it just to ensure that there wasn't any moisture leakage through the ends of the around about 1.5 metre long dummy stud. Also measured the CLT floor, and that was put through to the first laminate, midpoint of the first laminate, and that was measured in these locations. Humidity was also measured, and all of this data was sensors that were used was hardwired back to data loggers, and from the data logger, which was contained in the garbage room, they were connected by Wi-Fi to the what's called a big, and you can see here's a picture of the wires going through the buildings. Obviously, there's fire issues to deal with, so we had quite a large number of wires that we had to deal with for every story. And from the data logger to the laptop, which was called a big, it was Wi-Fi connected, and we had to put Wi-Fi antennas throughout the building just to be able to make sure they picked it up. And the big building intelligence gateway was nothing more than a laptop, which then connected, and this is a bit of a plan of what the wiring of the building, connected to the web, which is then was able to allow the clinical software to calculate the results. And this is what the platform looks like from the website, and you can see the number of sensors we have, and this is the type of outputs we can get, which is these squiggly lines, coloured lines. So we had 289 sensors installed, and all wired to the data logger, which connects to laptop via Wi-Fi and then onto the internet-based software. So what what was the results. We look at the data collection. The first census went into commission in October 2018, and the first report was made in June 2019, and the last data collection was about April 2020, but censuses were dying from early 2020, so the batteries were dying, and unfortunately it occurred mainly during the COVID period, so we couldn't do anything about it, and we're prevented from going to try to change on the batteries what we could. But this is the type of output we get, and this is a temperature exterior wall, exterior east facing wall, 3 stories. And here we have a couple of gaps in information where the collection of data didn't occur. You occasionally get that. And this period up to about June 2019 was the construction bit, and this is with the handover and the potential occupation. We're not quite sure if the particular locations were occupied. Some were and some weren't, and sometimes the data goes out to describe that. This indicated that the number of stories. So if we see this key to the side of this, and this is fairly consistent throughout the rest of the graph's going to show you. It'll give you more colour of what represents a story. So the temperature on the exterior south-facing wall, you can see it's pretty consistent. I haven't individually shown you the temperature in the report, which will be available from Forest Products Australia. That will be, and you can see they're fairly consistent and changing through the seasons. You can see there's maximum temperatures to minimum temperatures cycling through the year. This is a bit of noise that occasionally occurred. You get to pick up a bit of, occurred when they power up the building. So a bit of stray electricity current somewhere tends to upset the sensors. But temperature near the corridors, again, following pretty similar type of things as other sensors are doing, and also within the apartment. So they were measured, and this is just more showing you how they're cycling through, pretty much the same. And you compare it against the BOM data, the meteorology data. You can see that for the period of time, the maximum and minimum for the outside temperature, and we had a 50 degrees temperature variation between the maximum and minimum. So it was below 0 and almost 50 degrees measured at certain times. You can see that the temperature within the apartments was fairly regulated and wasn't getting those peaks. And again, looking at the external wall. So relative humidity is a very key indicator, particularly when it comes to moisture content. And you can see here it's changing through it. We get fairly large relative humidity during the early stages, but you can see it's fairly consistent, varying from around about 60, averaging around about 60%. And we found that it was drier in the interior of the building than it was on the outside, which is kind of like makes sense. It's picking up a bit of moisture from the outside of the building while the interior is not. So we look at the construction side, so it's obviously wetter, so high relative humidity during construction compared to the handover and occupation of the building. And we look at the interior of the apartment. You can see here there is some low numbers there, and that probably represents the apartment wasn't occupied. So comparing exterior walls with interior walls, we can find that the relative humidity is much less on the interior than compared to the exterior walls. So moisture content, and we're looking at this case now, is the corridor wall, and it's probably the driest bit. And we can see here the moisture content for a number of stories was varying around about from 10 to 16 to 18%. And during construction, enclosure of the building, and handover and potential occupation. But something happened here a little bit. I'm wondering what was going on there. So why did we suddenly get a rise of moisture content, which is a bit of a concern. And so we look at what that is. So if we calculate what that moisture content could be from relative humidity and temperature, we set it to around 17%. So we had to look at the data from other things around it. And there's moisture content of the dummy studs, relative humidity was only 55%, and temperature between 20 and 30 degrees. And that really should have been around about 8 to 10%. So so I'm not quite sure exactly what was happening there, but we had a closer look and we found that the battery was dying in that period of time. So some of the later data is corrupted by the battery not working as well, and it tended to jump up in certain places, so be wary of that. You can see here we've got some noise here for another interior apartment towards the end, and that was caused by the battery dying. So you can see here we are getting down to 10%, 9 to 10% in moisture content, but it can go up as high as 15%, and you can see changes from the construction through to the occupation. Again, just flicking through that, moisture content of that is around about 8 to 10%. So it wasn't an error in there's an error in the reading of the meter and moisture content in that particular area. Again, the battery expired. So moisture content of the east facing wall, pretty consistent, and also the south got similar type of results. Again, a bit of noise towards the end. But it's good to be able to see that they were fairly consistent throughout. And we also had the moisture content of the CLT floor. The light brown one was a bit lower, and the reason being that it's the 5th floor, well, that's actually the roof. So the roof panel was noticeably drier, and that makes sense because it's picking up a bit of heat from the roof above, and it was drying it out. So it's quite considerably different compared to the floors and lower down. But one of the interesting things was looking at what the difference between radiata and spruce. So the black line represents radiata, and the spruce is a green line, and you can see that there's a lag a little bit between spruce and radiata, but they pretty much follow the same changes in moisture content. And we look at the rainfall period. We can see this is the rain occurred during the period over that period of time, and we overlay that with the moisture content of radiata pine. It's a bit hard to overlay these two graphs here, but you can see that there's a spike occurring with the moisture content. For example, there, and this is a very large rainstorm occurred, and almost 100 millimetres of rain occurred in a couple of hours in Sydney. You can see there was a major spike occurring. But we look at the comparing the relative humidity, the temperature, and the moisture content. And you can see here that we got a drying of the 50% relative humidity with the temperature, and that resulted in a lowering of moisture content. So we can see that common sense is occurring in the data, that it's measuring what the measurements are pointing to what the actual data is. More interesting, what is happening in the displacement. So here's the measuring the displacement in the exterior wall for the northwest facing one, and pretty much quite unchanged for most of it, bar one. So in this case here, we're a little bit concerned about what was happening here because it was a 10 millimetres movement while the other parts weren't moving at all. So we had a little bit of closer look at that and found that the moisture content, the relative humidity was rather low, moisture content was low, but we also found that the temperature, something was happening there because it was measuring at -5 degrees. So we didn't think that ice was forming in the wall, one story during summer. So there's something data going wrong in that point in time. So we'd just be wary that the movement wasn't occurring. It was occurring as expected. And so it happens occasionally that these things don't measure correctly. Displacement exterior wall, southeast facing wall, we find again it's not moving very much. We measured at the last point -2.25 millimetres, and we also the table contains the maximum movement, so not really much at all. Much less than 6 millimetres that we expected per story. And interior corridor, which is the driest, which we'd expected to move the most because it's going to be the driest, -3.5, with some parts actually moving, expanding. So again, much less than the 6 millimetres per story. Again, be wary of the data towards the end, because you can see here with that particular string pot, there was a bit of temperature got a little bit crazy. So even interior apartments, pretty much the same. It got the most, which is the overall 12 millimetres, and that seemed to be registering the most correctly, but it's still less than 6 millimetres per story. And note this area here, which seemed to be a bit higher than usual. What we found there was the relatively high relative humidity at that point in time that caused it. But one of the things that Samir also alluded to, some of our data may be a bit strange because we had these blocks, which is what he was describing before, which were transferring the load from the stud walls onto the lower stud walls, and that took out the effects of the floors, and they occurred at random spots and mainly on the lower stories, or only on the lower stories, and sometimes it influenced our readings and other times it didn't. So it's something that is a note to self to look at where the location of those blocks are against where our measurements were occurring. And that's it. So summarising, the moisture content change, our estimate was 16 to 12%. Well, we didn't actually find that. We found that once the building was enclosed, it was around 16%, and we could say that's true. While it was exposed, it's getting direct rain on it, and that's where you're getting a high moisture content. So when it's protected, then we find this is occurring. Remembering that there's a moisture gradient occurring, which is something we need to do in our wood solutions guide to fix it up, because we need to explain that, particularly for mass type of timber. Moving points per story are around 6 millimetres are suggested, or from North American experience, but we found that it was a very conservative estimate, and was much less, around about 2 to 3 millimetres per story was probably more than the average of it, which shows you that it was a well-designed building, and congratulations to TTW for a well-designed project. Okay, so we're now at question time, and we'll take on the questions from 14 questions, and I'll start from the very beginning. And the first question from Scott: can you please repost the questions for the CPD? Yes, they will be done towards the end. Denise, did you also monitor the relative humidity in the instrument wall cavities? The short answer is no, that wasn't done. It was done at those locations only. And I'll get a question soon. Take time to explain the CPD questions. All right, we'll do that one when we go through CPD questions shortly. How is the rain during construction handled in relationship to the CLT floor? Samid, I'd like to, you saw the building more under construction than I did. Would you like to jump in and answer that question?
Yeah, sure. So I think generally speaking, Strongbuild found that from some of the construction experience over in Europe, they didn't really tend to do very much during heavy rain. Sometimes they would cover it in tarp, but there were occasions where they didn't. It really depended on the type, the duration of the rain. But generally speaking, they basically just left it out there. I think they got advice from the manufacturer that if it's just for a day or so in weather, it's not a major issue. They just usually let it dry out before they screed it over it.
Okay, thanks. And I think also it's you can see from the rain collection data that there was only occasionally rain. It's fairly dry out in Western Sydney, but I must admit over the last couple of days it's not been the case. Moving on, so when asked, okay, so what company did the off-site prefabricated LVL walls? That was a company which unfortunately doesn't exist anymore. That was Strongbuild. From Nice, what was done specifically in regards to moisture control? Another one for you, Samid. You want to answer that one?
So again, I think there wasn't anything overly specific that Strongbuild had done during construction. So what they really tried to do, I guess, was make sure that the ends of the walls were not left in puddles of water, or if there wasn't any water that was pooling over the CLT. But I don't think there was anything sort of major that they tried to do in order to prevent it. I think they mostly went off this concept of if it's only exposed for a short period of time, they weren't necessarily too worried about it.
Yeah, I'll probably enhance it a little bit. Yes, because it's all prefabricated, the construction time was very quick, so it was enclosed very quick, and therefore they tended to ignore any stormwater management and just let it go, because that's pretty much what's done with CLT buildings. Another question from Cameron: can you explain why the moisture content of timber element is higher on the lower floors in comparison to the upper floors? I'll answer that one. The only explanation is that it tends to, and you saw what the roof line was it was hotter, and it tended to be cooler on the lower stories because it was shading and things like that. So that's the only aspect I could see which is causing that. That would be explained for the exterior walls. The interior walls, there is no reason. What we haven't got as the data is the occupation of the buildings. So I suspect that not all all the units were occupied from exactly the day that the building was handed over. And so we don't know if the rooms, apartments were left vacant for a period of time and or not, and we'll have no way of knowing that because it's not, it's privacy issues in the sense that we can't get in there and ask people. So rapidly noticing we're hitting 12 o'clock very soon. And Denise, did you have to cover the CLT with gypsum board as well as the LVL to achieve performance on the fire limit states? The short answer is yes, the CLT was covered from the underside into the walls, and except for the interior of the core, which was left exposed. The fire LVL was fire rated, as you saw in the pictures of it in the factory, and delivered to site. So Jeff Morrell, good to see LVL being protected from termites. So what about the CLT? Can answer that one. Or Mead, any idea what termite protection was used in this building?
I think mostly that was something that Strongbuild did from memory. Their intention was to do a lot more sort of termite management, so they treated a lot of the entry points around the bottom of the building, and just tried to make sure that they had a regular set of inspections to monitor for any termite activity. Yeah,
and also add to it and there's actually a question we'll get to later, is that it's sitting on a two-storey concrete, half of the story is buried in the ground. So there's a concrete podium is acting as a giant termite barrier. It's well and truly built and braced for termite entry. You need to fairly adventurous termite to get up about a story and a half of concrete before it even gets to the wood. And when it does get to the wood, it'll hit the termite treated LVL. So and so that before it gets to the CLT, which is effectively going to be on the second story of the building, but the CLT wasn't treated in any way that I can remember. Sammy has a termite protection building sites on concrete podium. Why? I just answered that one. And the last question: what was the reason for using stud walls as lateral resisting elements as opposed to core walls? Sammy, again, one over you.
So a simple answer was because there were walls, so we figured we may as well take advantage of them. The other reason was the core walls. So the way Strongbuild actually wanted to do the CLT was they got them, they were provided by Binders, and Binderholz has this stand 125 wide panel. And for the core panels, they didn't want to get this big monolithic core panel. So what they did is they actually got these 125 panels and then sliced them together vertically. So what we find is that when they did that, there wasn't a great deal of stiffness in the core walls. So that was the reason why we didn't really rely on the core walls to deal with any of the lateraling. It was basically just the way that they tried to build it meant that they weren't acting like a typical sort of monolithic box section like you would in a standard core. And the other reason was just, well, we had all of this internal walls anyway throughout the building, and we just found it was a lot easier to design it that way as opposed to having to design the CLT diaphragm to then span everything back into the main core. Simplified a lot of the diaphragm detailing, especially because the CLT only had to span a few meters to the nearest wall as opposed to having to span the full length of the building back to the core.
Yeah, and also I'd add to that is that because the prefabricated wall systems also had that OSB on two sides of it and capacity, and a lot of those walls, I'm sure you must have found that a lot of that lateral resistance was gobbled up by those things anyhow, so you didn't need the core. Is that correct?
Well, essentially, yes, that's correct. It basically was like we needed the wall there to serve as an internal wall because we usually could put plywood on it and it would attract load anyway. It was just a lot easier to make use of it because it had to be there in some way or another, and it was a lot stiffer than the core, exactly, especially since the core was made of basically 125 wide panels all stuck together vertically, not like a 4 meter, 5 meter long panel. So the differential stiffness between, say, a 6 meter long LVL panel with LVL wall with OSB versus a few, 125 wide DLT panels that are stitched together with a couple of screws, the stiffness differential is more than the core actually probably wouldn't attract very much load anyway.
Okay, thanks for that. I think it's time to wrap this up. We hit past our 12 o'clock, and thank you, Samid, for all your assistance in this presentation. just a reminder of the CPD questions, and they again will be sent out. They've been discussed during this presentation, so you should be able to easily answer that. If you can't, just particularly one about the eco and wash content, just Google it. Just a reminder, Wood Solutions webinar series is available for you post these events. Just go to the Wood Solutions website and type in webinars, and you'll be able to go directly to where they're kept. There's a huge number of them now available, so please go back and relive some of this if you missed it. Apologies, I just jumped ahead. Next webinar is next Wednesday, the 4th of November. I gather people in Victoria tend to take a day off on the first Tuesday of the month, or is that just to celebrate the American election? I'm not quite sure, but and this is an exciting presentation. Gilly Recreation and Culture Centre. I actually think is an excellent project. This one, it's quite a simple project, but with the LVL and using modern quick connectors is such a stunning project for what it is, and it'd be interesting to hear from the architect involved in that project. So that's an interesting one. Just remember, it's Wednesday, 4th of November next week. So note the change in time. And just again reminding you about the Wood Solutions webinar series, and the CPD certificates will be sent out by email to you. Please store those, and it's your responsibility for that. And also, this is very important that to help us make these presentations better, there's a link here to the survey. It'll also be sent out with the email. And if you have time, please go there and fill out the survey, because it's very important to make sure that we deliver to you what you want. And at that point in time, I'd like to just say thank you, and thank you to Wood Solutions, and we look forward to seeing you at the next Wood Solutions webinar. And thank you for attending.